The railway line between Olten and Aarau is only 2 or 3 track and is the bottleneck of the 4-track line between Bern and Zürich. The line needs to be developed into 4 continuous tracks. In the area of Schönenwerd there is no room for 2 additional tracks. Therefore, Marti is building a 2-line bypass route for the Swiss Federal Railways SBB. The new line leads almost exclusively through the 3,100-meter-long Eppenberg Tunnel. The largest part of the tunnel, about 2,600 meters, will be constructed underground by a tunnel boring machine, TBM for short, that is over 100 meters long. This bored tunnel is only half of the work to be done. At each end up to the portals, construction will be carried out using cut-and-cover technology. A huge excavation was carried out on the slope of the Eppenberg at the eastern portal, where the TBM will later be assembled. For the construction of the cut-and-cover section, the slope was secured with a variety of techniques over a length of over 300 meters. The heavily used main road had to be relocated several times. The Schönenwerd railway station is located above ground on the existing line and must continue to be serviced in both directions. However, in the rail network, tracks traveling the same direction must always be adjacent to one another. For a crossing-free entrance into the tunnel, a single-track tunnel is built under the tunnel tracks. The construction of underground tunnels in a confined space between heavily frequented traffic routes, combined with the slope of the Eppenberg, resulted in an impressive and extremely complex construction site. Most of the cut-and-cover works take place on the narrow strip between the provisional main road and the railway line. More than 9 kilometers of bored piles were drilled for temporary supporting walls and for final structures. In addition, 24,000 square meters of sheet piles and soldier pile walls were required, an area equivalent to about 1/3 of a football field. Working with heavy equipment in the immediate vicinity of fast-moving trains and cars requires maximum concentration. In the area of the single-track tunnel, the supporting walls are up to 26 meters high. The actual tunnel is being built inside the finished excavation pit. The tunnel must later resist the pressure of the steep slope and is therefore extremely massive. For the concrete work, mobile formwork carriages were used. During the construction of the cut-and-cover tunnel, the mined tunnel driving started from the front area of the excavation. Initially, the tunnel passes through loose material which is not suitable for the TBM. The first part of the tunnel is therefore constructed using the canopy tube process. The tunnel is broken out under the protection of the pre-bored canopy in 10-meter stages. After about 60 meters, enough cover was achieved within solid rock. This means that the start-up tunnel is ready and the area in front of the tunnel is free for the assembly of the TBM. In October 2016, the cutting wheel was lowered and fitted to the tunnel boring machine. In January 2017, the machine started its journey through the mountain. During advancement, the disc cutters roll over the rock under high pressure on the almost 13-meter-high cutting wheel, thereby continuously breaking chips from the rock. Through the openings in the cutting wheel, the loose material falls into the wheel. The cutting wheel arms pick it up and transport it by rotation of the wheel to the conveyor belt opening in the center of the machine. During boring in dry rock, the material directly behind the cutting wheel has to be freed from dust. With up to 20,000 kilonewton pressure on the rock, the cutting wheel is moved forward by 48 hydraulic jacks and a pressure ring on the already built tunnel. After every 2 meters, the machine stops and pulls the pressure ring forwards. In the gap, 6 segments are lifted in place to form the tunnel lining ring. The upper segments of the ring are temporarily held in place by jacks. In order to strengthen the tunnel, the segments interlock with a grooven tongue. When the top segment is positioned, the side segments are pushed upwards until the ring is closed. The key segment is now inserted into the gap at the bottom. The tunnel segments ring is now self-supporting. After approximately 20 minutes, the machine returns to excavating. In the gap between segment and rock, mortar is injected into the bottom part of the tunnel through injection channels in the machine shield. The tunnel is now solidly embedded in the rock. In the upper tunnel area, the gap is filled with gravel through openings in the segments. The excavation material is carried away by a conveyor belt suspended from the tunnel vault. The TBM continues to move, continually pulling the conveyor belt along with it. At the other end of the belt, a new section is continuously released from the belt storage system. The segments for the next ring are continuously delivered to the TBM. These are produced in Marti's own factory. The filled formwork passes through a 55°C steam channel. For the 6 segments of a ring, there are also 6 formwork elements in rotation. For left and right curves, there are different dimensions of tunnel segments. The order of delivery from the factory already takes into account the development in the direction of the tunnel. When traveling through the Eppenberg, the machine crosses different geological layers. The Effinger layers in the east can be partly recycled and reused. The molasse sedimentary rock in the middle section of the tunnel is unusable and has to be transported away. The gravel layers in the west are very suitable for use as concrete aggregates. For this reason, Marti has developed and built a new gravel plant for the Eppenberg. The system is modular and can be moved to a new site in just a few weeks. In the plant, the broken out material is washed, crushed to gravel, and finally sorted according to different grain sizes. Material not suitable for concrete production is temporarily stored and later used for landfill and backfill. The unusable molasse rock is transported by truck to the refurbished waste disposal site in Kölliken as fill material. Marti was able to achieve a massive reduction in the number of truck journeys required for the project as a result of extensive processing and reuse on site. From the gravel silo, the gravel reaches the concrete plant by means of a conveyor belt across the railway line. The division of the construction site by the railway line and the main road make construction logistics extremely difficult. Through good coordination between the Marti companies involved, they have been able to develop efficient solutions and infrastructure. The tunnel will have 2 emergency exit shafts and a rescue tunnel. The tunnel was cast by using prefabricated formwork. The shafts were conventionally constructed from the top down. After 1,800 meters in a good 5 months, the tunnel boring machine has passed the Effinger layers and the molasse rock. The gravel layer that follows contains high amounts of groundwater. To ensure that the groundwater cannot enter the machine in an uncontrolled manner, it is retrofitted from dry to hydro-shield slurry operation. This retrofitting takes place within the protection of a specially designed board pile wall into which the machine has dug its own garage. During the slurry operation, the front part of the machine is sealed and pressurized. This support pressure counteracts groundwater and ground pressure. The front of the machine is filled with a supporting liquid, a bentonite suspension that is divided over two chambers. Compressed air in the upper part of the rear chamber acts as a spring and controls the support pressure. The material excavated by the cutting wheel is pumped out of the tunnel with the bentonite. There, the bentonite is freed from the excavated material in a separation plant. It is then returned to the TBM. During retrofitting, the conveyor belt was removed and the material opening was closed. The cutting wheel arms, which are now no longer required for material transport and would hardly be able to move in the bentonite anyway, were also removed. 1 week of intense activity in the cutting wheel. About 8 metric tons of steel from the cutting wheel arms were cut into transportable pieces and removed from the site. An elaborate pipe and valve system was installed for distribution of the bentonite in the cutting wheel and the excavation chamber. The feed and discharge of the bentonite is driven by high-performance pumps, pumping more than 650 litres of bentonite per second, mixed with soil, sand and stones up to 25 centimetres in diameter. This bentonite can become relatively thick, so Marti has installed additional pumps every 500 metres into the bentonite line. A separation plant was built on the site. Here, the excavated materials are separated from the bentonite in a complex process and fed on to the gravel plant. The suspended solids in the bentonite are separated out by filter presses and disposed of. Since the bentonite loses its solidifying effect with each cycle, it is continuously enriched with fresh bentonite. It is then pumped back into the tunnel boring machine. On the machine, the pressure ring is finally removed from the jacks. The hydraulic jacks must be individually movable for tunnel boring in groundwater. The pressure ring, weighing several tons, is removed from the tunnel in pieces by the segment carriers. After 8 weeks of retrofitting, the bentonite circuit and the tunnel boring machine were ready for operation. Hydro-shield operation in loose ground requires the support pressure to be selected in such a way that the bentonite penetrates the soil in front of the cutting wheel to compensate the groundwater pressure. The bentonite solidifies due to its clay properties, preventing loose gravel flowing uncontrollably into the cutting wheel chambers, causing ground subsidence above the machine. As the TBM moves forward, the solidified material is removed in a controlled manner. In the excavation chamber, fine-grained material dissolves in the bentonite. Solid components like stones sink to the bottom. Here they are broken down to about 25 centimeters in size and then pumped away together with the bentonite. During the driving operations, the support pressure must be continuously adjusted so that enough bentonite is injected, but not so much that it spreads to too much of the surrounding area. For this purpose, the volume of bentonite pumped out is constantly compared to the volume added during the same period of time, consisting of added bentonite and the tunnel volume driven by the machine during this period. The anticipated support pressure is calculated in advance for each meter, but there are always deviations, and for the TBM drivers, identification and correct adjustment of the support pressure are crucial. The control of the machine, taking into account all the parameters indicated by the TBM and the pre-calculated support pressures, is a matter for absolute experts. Due to the permanent changes in the geology and the limited material removal by the bentonite, the machine only moves forward with a quarter of the previous speed during the rock section. During the driving operations, the segments are prepared for the next ring. The construction of segments change for installation in groundwater. They now have sealing bands in order for the tunnel to be watertight. The segments must fit exactly together. Each segment is now positioned in a millimeter exact manner. If it fits perfectly, it's held in place by the jacks. In addition, the segments are bolted together. Since only the jacks for the segment to be installed are withdrawn, the segment rings are permanently held under pressure and therefore watertight during ring construction. With this, all segments are fixed in their final position, and the gap for the key segment must be exactly right. The key segment is conical and is pushed in from the front to its final position. The tunnel ring is finished and the machine returns to excavating. The tunnel is now no longer embedded in solid rock, but rather in relatively loose material, so it is completely grouted with mortar. The bentonite is in the gap between the ring segments and the rock, and the mortar has to be injected into the gap against the groundwater pressure. Its composition must be exactly matched to the rock and the respective injection pressure. The special challenge right before the end of excavation is when the TBM drives through the granular soil under houses, with only minimal cover to the surface. The houses and other structures above are permanently monitored. Then all the trouble spots have been overcome. At the end of 2017, the TBM breaks through into the target pit at Gretzenbach after over 3 kilometers of driving through the mountain. The cutting wheel and drill head of the TBM are disassembled and removed at this point. The last 125 meters of the tunnel up to the Gretzenbach portal were built using the cut and cover method. The roof of this tunnel is concreted first, and then the tunnel is excavated underneath. To construct the tunnel walls and secure the slope directly below the Gretzenbach church, extensive special civil engineering work was carried out. Once again, the main road had to be diverted several times to build the tunnel. Because of the buildings above the tunnel portal is 4 meters deeper than the existing section. As a result, there will be a 250-meter long ramp in front of the portal to align the levels of the tracks. Work on the Gretzenbach portal will be completed in summer 2019. The tunnel will be equipped with a sealing foil and solid tunnel lining. The Wöschnau excavation will disappear almost completely. Then the shell of the tunnel and its access routes will be completed. The construction of the Eppenberg Railway Tunnel is a highly complex process in many respects. Thanks to good coordination, the Marti Group is expected to hand over the tunnel shell to the client in the summer of 2019.